This is an example of how to work the problems in the Laplace Transforms game in Circuit Tutor on level 1. Laplace Transforms is found on the website rather than in the downloadable software. So we'll go ahead and go into Laplace Transforms. Now, normally you would begin by doing the tutorial, which I've already completed here, but that's basically a multiple choice type exercise that leads you through the basic ideas involved in Laplace Transforms. And that should be done prior to doing the exercises. So we're going to go ahead now and just play the game. And as always, we have examples available here at a variety of levels. It's always a good idea to look at that. And there's also a special feature here called User Selected Examples, which will allow you to pick particular functions to look at the Laplace transform of, which could be something that may not necessarily be included in the exercise. And you have the option also of making that time shifted, and then you could view that example. But we'll go back now and not do that. So I'm going to show you now the easy level, and there's 5 different problems on that level, so I'm going to show you an example of each. Again, looking at the examples would be a great idea. Here it shows you how to do, for example, t squared u of t. Takes you through all the detailed steps in doing that. And so it's a good idea to look at some of those before you start as needed. Okay, so let's begin an easy level problem. So the first problem here asks us to find the Laplace transform of 3t cubed u of t. Remember that anything we're going to take the Laplace transform of typically has a unit step function involved. So to do this, it's really very straightforward. We're going to use a table of Laplace transforms. So to access that table, you can always just click on the link here, and that'll bring that up in a separate tab. And so since we're looking for t cubed u of t, basically, we can look at that and find this formula here. So t to the n u to the t is n factorial divided by s to the n plus 1 power. So if n is 3, we have 3 factorial. Remember that a number factorial is the product of that number with all integers down to 1 that are smaller than itself. So in this case it would be 3 times 2 times 1, or 6, divided by s to the, if this is going to be 3, then that would be s to the 4th. So it's going to be 6 over s to the 4th. So remember that. And also there's a prefactor of 3, and as you may remember from the introductory tutorial, one of the most important properties of Laplace transform is the homogeneity or scaling theorem, which basically says if you multiply a function by a constant, you multiply the Laplace transform by that same constant. And that property follows directly from the fact that Laplace transform is defined in terms of an integral. So from the defining integral and the fact that integration is a linear operation, that gives us automatically the homogeneity or scaling operation, as well as what we call additivity, the idea that if we take the Laplace transform of the sum or difference of two functions, that would correspond to the sum or difference correspondingly of the Laplace transform of each function separately. And so together those two properties are known as linearity, and Laplace transforms are indeed linear. So that's something we probably want to just remember rather than having to look that up every time, because it's a very fundamental property. But we will have to use that here because we have 3 times t cubed u of t, and so that remembers that we just have to multiply 3 times that constant. So now we're going to go down here and enter, this is a palette-based interface, as you may have used in the downloadable software, and we can drag things into this palette, or we can just click on them, either one. Now we have to be careful because there's 3 different tabs here. This is things that are in the time domain, which are functions of t. And since we're trying to put g of s, clearly our answer is to be in the Laplace domain, or the s domain. So none of these terms will be useful and should never be used in the Laplace domain. Some of the ones that would be the same in those two domains will be reproduced on the different palettes. So you won't need this palette. Likewise, this one is for time domain functions that have been shifted in time. In other words, replace t by t naught, t minus t naught rather. And likewise, those are not useful since we want not g of t here, which we're already given, but g of s. So the appropriate tab here is the Laplace domain tab. So now we do need a fraction because remember that we found that this transform of this was just going to be 6 over s to the 4th. So we can either click on that or we could drag it into place. If you put something in here by mistake, you can always just drag it out and it'll be gone, and that applies to any of the terms. So like I said, you can drag or click, whichever. Now we'll need a constant in the numerator. So I'll just put that in there. That's a constant term. And then we'll need an s to the n in the denominator, because remember this is going to be s to the fourth. So we'll fill that in, and this reminds us that we need to put in valid values there, what kind they should be. So that's going to be an integer power. And then remember we have, this would be 6 over s to the fourth, as we determined again from, from the table that I went through before. But now it's multiplied by the 3, so that's going to have to be an 18. So we just put that in there, and then we can check the equation here. If at any time you need to give up, of course you can do that if you're unable to complete it, and it'll show you the answer. There is no penalty for giving up. It just means that you would have to then do another problem of the same type. And of course, if we mess up the equation badly, we can just clear the equation here. Okay, so we'll check that, and that is correct. And so there's also always going to be a detailed solution. Again, this is a very simple problem. You may not need it, but if you do want to see a detailed solution, that would be available here. And that would explain exactly how you apply the formula and plug in the numbers, basically, and evaluate things. Then that would give you show you how to get the answer. And also has some comments here about units being emitted in these expressions. Okay, so let's work another problem at the easy level, which will likely be different. So this time we're getting an exponential function times the usual unit step function, and e to the minus 4t multiplied times 10. So once again, we're going to use the linearity or homogeneity property of Laplace transforms to handle the 10. So that just means we'll have a 10 out front. Now you may remember the Laplace transform of e to the minus at. That's actually one that I would strongly recommend you do memorize, because it's used so often in doing Laplace transforms. So if we go to the table, we can see that the Laplace transform e to the minus at u of t is just 1 over s plus a. So in general, I would recommend that these first 3 transforms of the delta function, transform of that is just 1, u of t, that's just 1 over s, and of the decaying exponential function, assuming a is positive, is 1 over s plus a. Those 3 are used so frequently that I would really recommend you memorize those. The rest of them are optional, because you can easily look those up in a table, and some of them are a little bit more complicated. But those first 3 definitely should be memorized. Okay, so using this formula, then we're going to apply that. And so again, we need to be in the Laplace domain here, because it wouldn't make sense to do anything else. And we're going to need a fraction term again, so we'll click that. And then we need a constant in the numerator. The constant can be positive or negative. And then we have an s plus a term that we'll need there. And so we'll fill that in with the a is going to be the 4 from the exponent, since it's negative 4t. And then the numerator will just be the 10, because remember the Laplace transform e to the minus 4t was 1 over s plus a. So now we just check that, and that is correct. And once again, we have the detailed solution available if you need that. Okay, so now let's work another problem at the easy level. There are 5 total problems. So here we just have the unit step function multiplied by negative 12. Well, as I just mentioned, the unit step function, that's one that we should probably memorize. That the unit Laplace transform of that is just 1 over s. In a sense, it's a special case of the exponential where the a value is 0. That's another way of thinking of it, because you could actually memorize both of those together, but I would just memorize them separately. Okay, and then linearity implies we need to multiply by negative 12. So again, we need to be in the Laplace domain tab. We will need a fraction term. And so we'll just put a 1 in there, and I'm sorry, we'll put a negative 12 in there is what I meant to say, because we have the constant. So we'll backspace that and put in a negative 12. And then we have just the s term, and we'll just put that as s to the 1. And we'll check that, and that is correct. So these easy problems are generally pretty simple like this. And we'll do another one. So in this case, it's a little bit more complicated. So now we have t to a power times the decaying exponential times u of t. So that one maybe we need to look up. So let's go into the table, and that's t to the n e to the minus at u of t is the form that we need to use because this one doesn't have the exponential. So we need n factorial over s plus a to the n plus 1 power. So in this case, as you may remember, the n was 4. And so for the 4, we're going to have 4 factorial, which is 4 times 3 times 2 times 1, which is 4 times 6, or 24 in the numerator. And then we're going to have, since this is a 4, that will be s plus a to the 5th power. So again, we need to be in the Laplace domain, put in the fraction, and we'll put our constant in the numerator, and then the s plus a in this case to the n power, so we can have an exponent greater than 1. And that will be, again, to the 5th power there. Our a will be just the coefficient of t in the exponential with the negative sign, of course. So that's going to be the 12. And then remember we had a 24 from the n factorial here, but we also have a minus sign. So it'll be negative 24 by the linearity property. So we'll check that. And once again, that's correct. And as always, we have the detailed solution available if you need that. And let's do one more problem to complete this level. So in this case, it's just going to be the unit impulse or Dirac delta function. And as I had suggested you memorize, the Laplace transform of that is just 1. So that makes this very easy. Again, we just go in the Laplace domain, and the answer here is just going to be simply a constant, -6. So we just put in -6, and we'll check that, and that is correct. And again, we probably don't need the detailed solution here, but that would be available. So that completes the example of the easy level.